What's going on? My name is Tosh Dalday. This is SDG Labs. Welcome to class. Physics! South Carolina wide receiver Ashlyn Jeffrey skies over the defense and makes a catch for a Hail Mary pass and dives into the end zone for a touchdown. Assuming he ran at a constant velocity, and what is the minimum velocity you would have to have in order to make it to the spot where he caught the ball? Well, all right, here's what I would do. I would say, look, here's the quarterback. He throws the ball at an angle theta. Wide receiver catches it. Here's my range. Here's the quarterback. I'm going to assume that the quarterback and the wide receiver are about the same height, so they catch it at maybe the same height. You know, the quarterback throws it when he's up here, but the wide receiver, he kind of jumped up and caught it like right about here, so it's about the same height. If I have something starting and landing at the same exact height, then really, I guess my question what I was asking you is how long does it take for the runner to get out there? T equals what? How long does it take for the ball to get from point A to point B? And if it's starting and landing at the same exact height, then you can use what I call the range equation. R is equal to V naught sine theta, or sine of 2 theta, all over G. Is that correct? Does that units work out? Let's see. This is meters per second on top. This is meters per second squared on the bottom. So this meters comes out with that meters. This seconds comes out with that seconds. That's not, the units don't work out. Oh yeah, that's right. I screwed it up. It's V naught squared. That's a good way to check your work. Actually, to be honest with you, I screwed that one up on purpose. Screwed up writing on that equation on purpose, just so I can make sure that I showed you that, hey, the units don't even work out on this. It has to be something else. All right. If I have that equation, because that equation governs how far something goes, depending on how fast you throw it, and what gravity is and the angle that you throw it at. If I want to solve for the velocity at which you threw it at, you can just say, all right, well, the velocity is equal to gr over sine 2 theta square root. All right. Gr over sine 2 theta, let's take the square root of that. This is the velocity that he threw it at, so the velocity in the x direction is just whatever this is times cosine of theta. And if I want to figure out the time it took, I would say, well, this velocity in the x direction is equal to the distance that he had to run, so that r, divided by the time. And if I want to figure out the time, I just solve for t. And I end up getting r over v naught cosine theta. So it's just that. So it's t is equal to r over the square root of gr sine 2 theta times the cosine theta. Let's put that all into the same square root sign. So I'm going to make that squared and put a square root over that. I'm also going to make this squared and put a square root over that. And then what I'm going to do is I'm going to say, all right, t is equal to, see, one of this cancels out with that, and so I have r sine 2 theta divided by g cosine squared theta. I know that the sine of 2 theta, actually in order to get that I used a trig identity, which was 2 sine theta cosine theta. So one of those cancels out with that. And what's interesting is I've got a sine of theta over cosine theta, that's known as tangent theta. So my time is equal to the square root of 2r tan theta all over g. And what I thought was really interesting about this time, let's write that up here. The square root of 2r tan theta What I thought was really interesting about that time is, if he, actually, you know what? Before I start describing and talking about this time, why don't I solve for the velocity that he needs to run to get there? So the velocity that the runner needs to go, the velocity of the runner is equal to the distance that he has to travel divided by the time. That's the time. So it's equal to the velocity of the runner is equal to r over the square root of 2r tan theta over g. So let's pull the same trick. So we have Vr is equal to the square root of g over 2 gr over 2 tan theta. Here's what I thought was really interesting about this. You have domain issues again. Your domain, your denominator can't have a 0 in it. When does tangent become 0? Well, it's when theta equals 0. If theta equals 0, then tangent becomes something bad, and this whole, this thing becomes a problem. Well, what happens is, that's saying that if he threw this at horizontal, then it wouldn't really go anywhere, and the runner wouldn't have any velocity to run at because you have a domain problem. The problem kind of explodes. What happens if theta were 90 degrees? Well, in that case, then tangent of theta is infinity. So we can't really get theta equals 90 degrees. Let's make theta get very, 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 very close to 90. That would mean this number gets very, 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 very big on the bottom, which means the overall number gets very, 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 very small, and you take the square root of it and it even gets smaller. So the velocity of the runner has to be really small. I mean, if you think about it, if I'm throwing this thing up at 89 degrees, how fast does this guy need to run in order to catch it? Not very fast, because he just has to kind of go, oh, there we go, I caught it. If theta equals 1, all right, that would mean I'm throwing it at 45 degrees, which is what I assumed in the beginning. So then you just let theta equal to 1, or tangent of theta equal to 1. Then you end up getting the velocity of the runner is equal to the square root of gr over 2. Now, technically, you could, and a lot of you did this. In fact, none of you did this. All of you did this. You said time is equal to 6 seconds. Where did you get 6 seconds? Well, you watched the video, and you notice that 6 seconds into the YouTube video, when after the quarterback yells hike, the guy catches the ball. Is that correct? Yes, absolutely. That's correct. It kind of tells me that you're more of an experimentalist than a theoretical person, a theorist. That's not completely bad. It just means you guys, you like performing the experiment more so than you like doing the theory. That's the difference. Now the theory is actually super accurate and whatever. The experiment is actually super accurate too, because the theory didn't take into account the difference in height of the football players, the fact that maybe the theory didn't take into account like air resistance, all of that kind of stuff, which the experiment did. But there's also disadvantages to doing it on the YouTube video, because that might not be super accurate. I mean, you could start and stop, do as a stopwatch, but even that, you'll have problems with like accuracy. So technically, I don't know, either or is right. I am actually kind of a big fan of this way, but I'm a big experiment guy too, so I don't know. Shoots, bro, up out.